Okay. Good afternoon again, once everybody. My name is ETH. I'm a software engineer and a blockchain developer. I'm here to give us a walkthrough, a hands-on on the computations for zero knowledge. Now, I'm sure as we've been informed, zero knowledge is a concept in cryptography that represents a way for one person to prove or rather to prove that they possess a certain information without actually revealing this information. Now, how does this work? The mathematics behind it is highly dependent on polynomials. So the concept of polynomials and cryptographic techniques is used to ensure that someone can actually prove to have to possess information without actually revealing this information. So how does this work? First and foremost, zero knowledge follows a certain procedure where the first step is the setup. And now this is a public statement by both the prover, the person who claims to possess this information, and someone who verifies, the verifier, the person who verifies this information. So the first step is actually to set up. This is often a public statement, like I mentioned before. After that, there's an initialization, and this is where the verifier initiates a challenge to the prover, right? So that if the prover gets this challenge right, it can be verified against the information or knowledge that this prover or the person proving claims to possess. Now, generally after that, you have the proving and of course the verifying, and then this process can be repeated oftentimes, right? So that the more you repeat it, the more accurate it tends to get. So there are a lot of mathematics behind this, right? So there've been a couple of protocols that have been developed over the years. Example of it is of course the modular arithmetics. Of course, we uses the same concept I mentioned earlier, polynomials, right? So actually it checks for a range of numbers called modulus. It checks within this range of numbers if this person has what he or she claims to, the information they claim to have. It uses polynomials to put this to action. Of course, with polynomials, you can actually check without actually, you can check to verify without actually knowing the secret of that. Also, we have elliptic curve cryptography is also a concept in zero knowledge protocols. That here, the elliptic curve cryptography generates a public and a private key, and this public and private key can prove that this prover actually owns or possess knowledge of what he or she claims to possess. There are also interactive and non-interactive proofs, which of course I'll be showing us in a bit how this works. For the non-interactive proof, we have a concept called the ZK snacks. The ZK snack stands for zero knowledge, succinct non-interactive argument of knowledge, right? It's just a specific class of mathematical protocol that is used in zero knowledge proof. They are both mathematical concept I talk about, polynomials, and of course, modular arithmetics is actually utilized in ZK snacks to actually prove that somebody has knowledge of what he or she claims to have. So I'll just show us a simple implementation of how this can be achieved using Python. But generally, the concept of zero knowledge is much more complex. But let's look at how this can be actually achieved. Remember, I mentioned that all of this follows certain procedures. So let me just share my screen. So all of this follows certain procedures. I have a file I already set up. I don't know. Okay. So I have a file I already set up called zkp.py, like I mentioned before. And here I'm going to actually, first of all, try to prove that I actually own or possess information about a particular number. So how this works is we are going to follow the steps as I mentioned. We set up the phase, we then commit, they call it the key generation, which we commit, then we prove, then we allow the verifier to verify. So, okay. So for this, we are going to make use of, let's say, first step, right? So let's set up the phase, set up phase, like I mentioned. Here we are just defining public parameters. So usually this setup phase is public. So let's take a number, for example, say P is 23. This is our setup phase. It's not our secret, right? It's not the information we claim to possess. This is visible to both the prover and the verifier. So let's say 23. Why 23? Because 23 is actually a prime number. So then we will have what we call a generator, which I'll denote with G. So let's say our generator is 5. This is our generator. I'm just commenting this out so that we can follow along. Now, let's say I claim to have a secret, right? So the prover's secret. So let's call my secret X, right? So let's say my secret is number 7. It could be anything. It could be an NFT. It could be information. It could be anything on the blockchain. But I'm just saying that for this case study, my secret is number 7. Now I need to prove that I actually know this secret. I need to prove my claim of knowing or owning this number 7 without actually revealing that the number I'm claiming to have is number 7. So how does this work? First, like I mentioned in the steps, we are going to have a commitment. Here, the prover, which is myself, is going to have a commitment that commits a value. I'm going to commit a value without actually revealing that value. So commitment, right? Commitment. So let's say I'm committing here, let's say the prover, which is myself, commits to a value without revealing it. Okay, so I'm going to call this value, let's say number 11, right? Let's just use 11. Just putting this is actually a random number. You could commit anything, it's random, right? It's not actually my secret, but it's a random number here. So the next thing now is that the verifier, of course, is going to present a challenge, right? Like I mentioned in the steps earlier, right? Why the challenge? The verifier has to actually use the challenge to ensure that the prover cannot construct a valid proof unless they have legitimate knowledge of the statement or the claim they claim to have. So the verifier in this case, let's call this challenge. So here we are saying that the verifier sends a random challenge. Of course, this challenge is also public knowledge, is public to both the verifier and the prover. So let's call our challenge, let's say challenge is equals to 1, right? So this is public knowledge. So now we need a response from the person proving, we need a response from the prover. So using our challenge, we are going to, of course, check sorry, just right here, after generating the random number, for the commitment, we didn't actually commit this number. So we have to commit this number because this commitment is what we are going to use to verify, right? So let's call this, let's say commitment as it is. Commitment is, here, this is where the polynomials come in. So we are applying a concept of mathematical arithmetics here. So we are saying that g raised to the power of r. Remember, r is our main secret, right? It's the secret we do not want to reveal. So using polynomials, we are saying that g raised to the power of r modulus p. Remember, p is also public, is a prime number, and is visible to both our verifier and the prover, right? So let's say these are commitment, right? So basically why we are committing it is that so that this value, like I said, the challenge from the verifier is to ensure that the prover cannot construct any valid proof unless the legit have that proof. So after that, of course, this is our challenge. So the next thing we need to do is to get a response from the prover, of course. So let's call this response. So let's say the response, the prover rather, the prover response to the challenge. So, all right. So now you are saying if the challenge, right, is equals to 1. Remember, our challenge is 1. So if our challenge is equals to 1, we want to return our response. This response will be this our random number, which of course we have committed that number. Remember, we have committed it. So we are going to return our random number back to the verifier. So we say that response is equals to R, which is of course our random number. Now, this is the response the prover is sending back to. Let's just make a check. If we don't get the response, what do we want to return? We want to return a polynomial that will actually tell us that this is wrong, right? So we're saying that of course, our random number, our committed number, plus our secret this time around, then the modulus of that by our prime number, which we had before, -1. This is polynomial. So this would actually return to us that this is actually wrong, that maybe the prover is trying to manipulate the system or something. So after getting this response, the next thing we need to do is to verify this response. Like I mentioned before, we are using the polynomials, which is widely used in zero-knowledge protocols. A lot of zero-knowledge protocols rely mainly on modular arithmetics, polynomials, because like I mentioned, polynomials gives the ability to actually check something without actually revealing what you are checking. So for our verification, let's say here the verifier. Here the verifier is actually checking the response to see if it is valid. So let's call this also verification for clarity. Then we now say that for our verification, remember when we're committing, we use polynomials to commit. So same also, we are using polynomials to actually verify this information. So here we are saying that our generator, which we had earlier, remember, this is our generator and our prime number, which was our setup phase, which was agreed. Now, if you check carefully, you see that the prover made use of the prime number and the verifier is making use of the generator, right? All right, so I just wanted to point that out. So we are going to also do similar thing, just like during the commitment, where the prover had to commit this generator by his own secret. But now, since we do not know the secret, but we want to check the secret, we are going to actually do that against the response we are getting, right? So against the response, of course, we are going to have a modulus of the prime number also. So at this point now, we are verifying that this statement that this prover is trying to prove, that this statement is true or is false, depending on if the prover legit has this information. So the next thing we now do, we say if our verification, now we're just cross-checking, is equals to the commitment, right? If the verification is the same thing as the commitment, what do we do? Let's just print, let's say, success. Sorry, let's just make it a string. Success prover as legitimate. All right. So let's just print that. And if this is not valid, if the prover doesn't have what he claims to have, let's just print, let's say, failed prover does not possess information. Okay. So basically, this is a simple overview of how we can actually use polynomials to actually check if a person has a particular number or not. Let's just save this and let's try to run the code. Let's try to run the code. Given that we all know that already, okay. Okay, so let's just run the code. So basically, I don't know if you can see, we're having a success that the prover has legitimate claim. Now, what happens if we try to change, for instance, the challenge, right? Let's try to change the challenge. Let's say he got the challenge wrong. So if we try to run the code again, you see we are having that it has failed, that the prover doesn't have this information. So basically, what we did here is we're using our knowledge of course, which every other ZK protocol uses, the highly knowledge of polynomials to actually verify that a user or a prover has information that he or she needs, though he or she claims to have, rather, sorry, he or she claims to have, we can actually check against that. Now, you can be saying, this is numbers, how about strings, right? So it's basically the same thing for strings. We just have to, okay, let me just comment all this out. It's basically the same step. Let's try it for strings. Let's try it for strings. So for strings, of course, we have to use a cryptographic hash to actually hash the string so that we can have a format to work with actually. So the first thing we have to do is to import a Python library, hashlib. Yeah, we should import hashlib first. Then just like the first step, right? Let's say this time around the prover secret, right? Let's say the prover secret. Let this be equals to, let's say, secret string. Let this be equals to prover's secret string. All right, so this is the secret. I, as the prover, claim to have a secret string. So just like the initial step, of course, the next thing we have to do is, of course, to commit this. And when we commit this, so that our verifier can actually check to make sure that what we have said we have it, we actually have it. So the next step is actually to hash this string so that we can have hexadecimal format to work with. So let's say um, let's hash the secret to create a commitment. So this actually creates, so to create a commitment, right? So all right, so we see that our commitment this time around is equals to hashlib dot we're going to use the SHA-256 encoder to encode it. Yeah, we are going to put our secret, then we encode it. Yeah. Right. Then the last thing we have to present it as hexadecimal. So we digest it. So we have an hexadecimal encoded hash. All right. So the next thing, of course, is our challenge. We'll keep it the same. Let's say our challenge is equals to 1. Just like the previous steps, but the difference is that this is a string and that was a number. So the next thing we check if our challenge, the next thing we do is to send the response, back to the verifier. So our response, in this case, here, remember the response is actually the prover responding to the challenge, right? The prover is responding to the challenge. All right. So we say that if the challenge is equals to 1, what do you want to do? You want to get a response, and the response is our secret key, of course, secret string. So we are sending back the secret string. So else, let's just have an else statement. Else, we should respond with something like, let's say, not a secret. Okay. So, all right. So the next thing we have to do is to verify. We verify this response. Say verification. Of course, remember we actually hashed our secret, right? So that we can actually use a hexadecimal representation of the string, which of course, since we're dealing with blockchain, is always advisable. It's not just advisable, is best practice to always hash all your strings. Anything you can hash that you don't want to review, you should hash it and then compare it instead of just having it out there. So what we are doing now is we are going to actually hash the response and compare it if it is the same with the commitment. So here we are going to use, of course, hashlib. Same thing we did when we're encoding it. We're going to get the response. Then we're going to encode the response to hex so that we can compare it with our commitment. So, all right. So after verifying, of course, we check if the verification is the same as the commitment, right? So if it's the same, let's print just successful. If it's not the same, let's print unsuccessful. So basically, it's just the same step as it's just the same. I don't know. I think I should increase this, right? So view. Forgotten how to do this. To like, okay, all right. So basically, let's just run it. I was trying to make this font bold. Forgotten. It's okay. It's fine. So let's save this. And of course, remember our secret. We are saying we have this secret and we've committed it, and we now need to, we are sending a response back to the verifier, and then the verifier is verifying our response here. These are responses verifying. So, and then it's now checking if the verification is the same as the commitment. So if we should run this again, yeah, we're having that is successful actually because we actually have this, right? So if we didn't have this and we claim to have it, normally this is very is more complex. This is just the mathematical overview, right? So most of these verifications in the real world, most of these verifications is done with high cryptographic techniques. Both the commitment and the verification it usually involves high cryptographic techniques, but all these techniques solely rely on polynomials, right? They use the same concept of polynomials that you can actually compare values without knowing the values, but you can compare it, and if this value is the same as this one, you can get them. You can actually check and verify that the both values are the same, right? So that concept of polynomials where you can check, even if you don't know the value, but you can check if the value is valid, is basically the basic base rock for all zero knowledge protocols and the mathematics and calculations and computations behind all of that. I think that's that from me. Except you have any questions, you are free to ask. Any questions for me? So basically, okay, I'll just go over the whole concept. The basic steps is the same, right? It's the same for everything. You first of all have your setup phase. Here you are declaring a public statement that between the verifier and the prover, right? That you actually possess or know a certain knowledge, or you hold a certain NFT, or you have so tokens, or you meet a particular criteria based on it could be any criteria, right? So you are just trying to prove to this verifier that you actually have this thing, but you don't want to show it. You don't want the verifier to have access to the real information, but you want to prove to this verifier that you actually possess this information. So zero knowledge proof is it's just a basic innovation that came up that is widely used in blockchain today. We have a lot of protocols actually using it. I don't know if you know about Zcash, ZEC. They actually use zero knowledge proof, right? So they kind of like protect user privacy, right? So and all of this. So they use zero knowledge proof to ensure that you can actually check that somebody sent a transaction, but you cannot know the value of that transaction. You don't know where it's coming from, and you don't know where it's going to, right? So this kind of helps you to verify that, okay, this person has this thing. And then if it meets your criteria, depending on your criteria, you can then, after verification, you can then either grant access or whatsoever you're building on the blockchain. So still waiting for questions. If anybody has any questions, feel free to drop it in the chat. Okay, so.
Can we check the YouTube if there are questions?
Okay.
So while
Let me.
So if you have one, just share. We have better. So let's just give us some such. Okay. No questions. Okay.
No questions. Okay. That's fine. So that's it for me. Thank you for having me.
So okay, so thanks so much for making our time to share your words of knowledge to us. We'll be going through the videos as well. They will be going through the videos as well, and then we're adding everyone to the Telegram groups. So any question that comes around, we could always tackle it over there. So once again, from the Portharcourt, we're giving you, let's just how do we hail him? Let's hail him.
Thank you very much. I appreciate it. Thank you for having me.
Okay, I just dropped the link to the source code.
Okay. I'll do that.
Yeah, okay, that's fine.
All right.
I think for now that's all so far. Thanks, man.
Okay. Thank you for having me once again.
So what's next? So